Hi guys, how you doing? Just wanted to clear up a couple of things that we went over in class. First of all, between the three tests, all right, easiest way to find out what test you're using. First of all, for goodness or fit, remember it's going to be a single categorical variable, okay? And it's from a single population. So it's one categorical variable, one population, which means it's just a one-way table. Now, don't get confused. It might have the observed values and the expected values, or it might just give you the observed values and want you to figure out the expected values, but it's just going to be one row, basically, of data that they gathered, all right? One row of observed values. All right, so this null and alternative can say a lot of different things. Sometimes it says like the distribution of blank is the same as the claim. Alternative, the distribution of blank is not the same as the claim. It could say a lot of different things. It kind of depends on the question that they ask. All right, so that's goodness of fit. Homogeneity. All right, that is one categorical variable, but that's from the result of two or more populations or possibly treatments. So it could be like two samples or two random assignments. All right, so that null will say there is something like, again, this is just an example. There is no difference in the two distributions of whatever and whatever. And right here, the alternative, there is a difference in the true distributions of whatever and whatever, okay? So again, one categorical variable, we're talking about two or more populations of treatments. Independence is two categorical variables, but just based from one population. So that's either one sample or possibly one random assignment, more than likely probably one sample. All right, and that's, in general, right here, an example, there is no association between whatever and whatever, and their alternative is there is an association between whatever and whatever. Okay, so let's see if we can figure this out based on some examples right here. Let's see here. Separate random samples of residents of Australia, United Kingdom, and United States were asked many questions, including the following. Some people say that the following things are important for being truly surveyed country nationally. Others say they are not important. How important do you think it is to be able to speak English? The two-way table summarizes the responses to this question. Do these data provide convincing evidence at the alpha equals 0.05 level that the distribution of opinion about speaking English differ for residents of Australia, UK, and US? Do these data... Okay, sorry, that's the same thing I just said. By the way, I forgot to say one thing. Goodness of fit is a one-way table. Both independence and homogeneity are going to be two-way tables. So we know automatically, since this is a two-way table, okay, automatically we know this is either going to be independence or homogeneity. Which one? Well, I'll tell you what. It says that we took separate random samples of residents of Australia, United Kingdom, United States. Right, so three separate random samples. So that tells me immediately that we are talking about homogeneity. Okay, so the null hypothesis right here. We're talking about the distributions, homogeneity. We're talking about all these distributions right here. So we're going to say, right, and the question asks, does data provide convincing evidence that the distributions of opinion about the speaking English differ for residents of Australia, UK, and US? So we'd say there's no difference in the distribution of opinion about speaking English for residents of Australia, UK, and US. Alternative, there is a difference in the distributions of opinion about speaking English for residents of Australia, the UK, and US. Alpha is 0.05. Okay? All right, so all good right there. So that is, and again, right here, once you're going to do the plan, don't forget right here, once you do the plan, you do all the conditions, the first thing you say is this is going to be a chi-square test for homogeneity. Okay? Okay. Now, for this particular one, how would I do, once I'm at the, first of all, just to get the expected values, how would I do that? Now, if it just has the expected value for like one single expected value, that's not too bad, right? Let's say you wanted very important in UK, right? So this one right there, if you want that. How would I get that exactly? Well, what I would do, remember, if it's just a separate one, I would just get that entire row value, put it over the total value, and divide it, and then multiply it times 1,460. So if if they just ask me specifically for very important with UK people who think it's very important about speaking English, that would be, once again, 2569 over 3463 times 1460. Now, and you get whatever that is. Now, the problem is that takes a lot of time if you need all of the expected values, which you do for the planning stage, right, for the conditions. Okay, so what you would do right here. All right, for these two-way tables, for both of them, independence and homogeneity, you have to do a matrix. You go to second matrix. You figure out this is a 4×3 table, right? So I go edit right here. And I put 4×3. Okay, I go to stat, go right here, and this is just regular chi-square test, which is letter C. So I go to stat, and then I go all the way over to test, chi-square test, because this is just for homogeneity, right? Homogeneity and independence is just that letter C, chi-square test. Okay, observed A, expected B, press calculate. What did I do right here? Divide by 0. All right, let's see. Maybe I put something in wrong. Hang on. Second matrix. Get out of here. Second. All right, so this is good actually because it shows you right here. So it's make sure I have everything right. 4×3. Oh, sorry, I'm an idiot. I didn't put the stuff in yet. My fault. All right, so it's a 4×3. Sorry, so I put everything in here, right? I would put 690. Okay, then I would put 1177. 702, okay, and then I'd have 250, 242, 221, 40, 28, 50, 20, 13, and 30. All right, so and then double check that you have everything accurately, right? Just move it right next to it. Looks good now, I believe. Okay, make sure, remember, don't ever put the totals in. Okay, so it looks like we're good right here, so we're going to go to back to stat, tests, and we'll do it right this time. Chi-square test, good. All right, A, B, calculate. Now, this actually gives us my do section, right? My chi-square, all right, my chi-square value, which is actually a really, really, really large chi-square value right here. I'm not sure why that is, but make sure that I put everything in right. And then you have the chi-square value, of course, and you have the, all right, it was supposed to be 68.57. So obviously I entered something in wrong. The p-value was only supposed to be, is supposed to be very, very low, but not quite that low. So just double check right here. I obviously put something in wrong. So let's go and double check here. Okay, 690. Oh, here it is. Yeah, don't do it too. Yeah, the problem with this, obviously, the virtual calculator, it's sometimes it does not enter stuff in correctly as I punch it in. 1177, 702, 250, 242, 221, 40, 28, 50, 20, 13, and 30. So how did I know that was an error? All right, so this is good actually in case you happen to type something in wrong. But how was I sure that this was an error? So I went back to test, right? Okay, so now look, we have, now it's large, but it's not that large. I think before, what was it? I already forgot, but it was in the hundreds, and that is so rare to have a chi-square test in the hundreds. The degrees of freedom, remember, is your mean. So this one's way beyond it. But one in the hundreds I've just almost never seen. So I knew something was wrong. This is pretty extreme also. All right. So anyway, point of being is right here. That gives you everything. A chi-square value, your p-value, which, by the way, when you write this down, I would just actually write down p is approximately 0. Okay. Is fine. Okay. Because this is like 0.000, you know, you have 12 zeros and then an 8. So it's approximately 0. Degrees of freedom 6. You write that all down. Now the point is, how do I get the expected value? I go to second matrix, go back to edit. Remember, A was your observed, B is they generate the expected value matrix for you. Just press B, and there are my expected values. So remember, in the conditions, the plan section, you have to make sure all of these are greater than or equal to 5. So you would recopy it and just put, all expected counts greater than or equal to 5, which they are. Okay? All right, so we are set with homogeneity. All right? In this case, the p-value is approximately 0. Okay, remember, p-value low, reject H sub O, and yes, we do have convincing evidence that the distributions of opinions about speaking English differ for residents of Australia, UK, and US. All right, let's go to this one. All right, this is what we did in Class A. This one was a little tricky, but there's one real huge giveaway that this is what type of chi-square test this is. Let's look. A study was performed to determine whether or not the name of a course had an effect on student registrations. A statistics course in a large school district was given 4 different names in a course catalog. Each name corresponded to the exact same statistics course. A random sample, one single random sample, okay, a random sample of student registrations recorded, and the results are given below. There they are. This data suggests the name of the course has an effect on student registrations. Conduct an appropriate statistical test to support your conclusion. Use an alpha equals 0.05. Now, I can understand if you thought this might have been independence, but there's one thing that gives away that is definitely goodness of fit, and I'll tell you what it is. First of all right, we have one random sample. Now, that could be goodness of fit, or that could be independence, but it is one single categorical variable right here, which is the number of registrations, and most importantly, it is just a one-way table. That is, it just has the observed values. Even if it showed the expected values, which, by the way, the expected values for this, well, if the names don't have an effect on, if right here they're saying that the course, the name of the course does not have an effect on student registration, then the expected right here, I'll just go and put this right here, the expected values, let's see here. If there are, how many people that took the course? 117. Divide that by 4. So 117 divided by 4 is going to give me what? 29.25, right? So the expected values right here, let me just make this better, more neat, there we go, is that it's going to be 29.25, 29.25, 29.25, 29.25. All right, and under the plan section, you would just say that all expected values are, you would show this right here, that the expected value is all expected values are 29.25, which is greater than or equal to 5, and that would be just fine, okay, for the large counts condition. Anyway, right here, okay, so this is a chi-square test of goodness of fit. Now, when you're doing the calculator for goodness of fit, the calculator stuff, all right, first of all, you do, well, actually, let's do the null hypothesis, right? It says, does the data suggest the name of the course has an effect on student registrations? So we can just kind of parrot that. The name of the course does not have an effect on student registrations, or registrations. And the alternative, the name of the course does have an effect on student registrations, using alpha equals 0.05. Make sure for plan, the first thing you say is, remember, we're talking about a chi-square test for goodness of fit, G-O-F, okay? No problem. One thing that we want to do for the calculator on this, it's a little different. For goodness of fit, it's only a one-way table, so we just actually go, remember how we do this, we go to stat and we just go to edit, and we're just going to go and put our information in L1 and L2. So clear it up, remember, highlight there, clear it up. All right, L1 is right here, 25, 22, 30, 40. And L2 is our expected, which I already entered in there. That's why it's nice to put the expected right next to it so you don't mess up. And that's just all 29.25, right? Oops. Yeah, this virtual calculator is nice and everything, but it makes a lot of mistakes from the keyboard. Okay. All right, so we have everything right there. So in this case, we go to stat, test, and this is goodness of fit. So right here, notice letter D right there, GOF, L1, L2. Now, degrees of freedom, is this going to be your categories? Like I said in class today, it's the categories. So DF, or in this case, is your categories minus 1. Okay? So in this case right here, we have 4 categories. So it just so happens that it already had 3 there. But yeah, it's going to be N minus 1, which is 3. There we go. And there it gives us. It also gives us, if it asks you which contribution contributed the most right here, it looks like the first one, it's kind of a pain to do this, but is 0.617. The next one is 1.797. The third one is 0.0. So it's obviously the second one. Oh, wait, I'm sorry, I didn't go to the fourth one. 0.019, and the fourth one is, oh, I'm sorry, it's actually the fourth one, which is 3.95, right? All right, so anyway, yeah, if a question does ask that, there you have it right there, okay? Or you could just figure out just by observed minus expected squared divided by expected. Anyway, this is goodness of fit, so that kind of covers everything there. The one thing I realized I did not say is right here, I think the calculator gives you the degrees of freedom once you put the matrices in, but if it's just one separate question, remember for a two-way table, don't forget degrees of freedom is just going to be rows minus 1 times columns minus 1. Okay, so in this case it would be, that's 4 minus 3 minus times 2, which is 6. All right, so just don't forget that. All right, let's go to this next one right here. In Chapter 1, you read about a random sample of winter visitors to Yellowstone National Park. Each of the 1,526 visitors in the sample, one single sample, was asked 2 questions. Do you belong to an environmental club, like the Sierra Club? 2, what is your experience with a snowmobile? Do you own, rent, or never use? The two-way table summarizes the results. Does data provide convincing evidence of an association between environmental club status and type of snowmobile use in the population of winter visitors to Yellowstone National Park? So this right here, we have one random sample. So that narrows it down to remember goodness of fit or independence. But right here, the reason this is not goodness of fit is, well, there's a couple reasons. One, this is a two-way table right there, so we know that this is independence. Also, we have right here, remember what I said about independence. It's 2 categorical variables that we're comparing with one population. So we're comparing right here the environmental club status and whether they have rented a snowmobile before, all right, a snowmobile experience, okay? But yeah, real quick, you just know, since it's a two-way table right here, which you're comparing right here 2 categorical variables, all right, you know that this is going to be a chi-square test. You can use the symbol, by the way, if you want to. It's up to you. For independence. Independence. All right, that's it right there. Okay, so how do I put this right here? So it's a lot of times it's really easy. You just answer their question. Does it provide consideration from association between this, right? So no. There is no association between environmental club status and type of snowmobile use in the population of winter visitors to Yellowstone. Alternative, there is an association between environmental club status and type of snowmobile use in the population of winter visitors of Yellowstone, using alpha equals 0.05. Okay, so this, though, the actual, calculator part of this is done just like homogeneity. All right, we just go and remember, we just go and do second matrix. This is a 3x2 matrix right here. So we put second matrix, edit, and this is 3x2. All right, so that puts everything right there. So we just put everything in here, 445, 212. I already made a mistake here, 445. Don't worry, on your actual calculator, it's much easier to put this in than this virtual calculator. 497, 77, 279, and 16. Okay, let's just double check. Yes, 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 yes. Looks like we're good. Okay, awesome. So we go to Stat, Tests, and this is just regular old chi-square test. Press Enter. It's going to fill out the expected for you. Press Calculate. So this is the do section. The chi-square value is, once again, very, very, very high. All right, so just make sure that you didn't make any type of mistake right here, and I'll go check that right there too, but I believe I did everything right. Let's see here. Yes, this is right, 116.6. That's a huge chi-square value. The degrees of freedom is only 2. So, you know, this is just a weird example where, in this case, the p-value is, once again, super low. So again, if you have something like this, just put, once again, once you're at the do section, your p-value is approximately 0. All right, much better. Awesome, okay. Degrees of freedom, it filled out too. How do they get that? Remember, it's the row minus 1 times the column minus 1. The rows is 3, column is 2. So 3 minus 1 is 2. And 2 columns, 2 minus 1 is 1. So that means the degrees of freedom is just going to equal 2. Okay? So they got that. Anyway, so that is everything right there. Let me know if you do have any more questions with this, but hopefully it's covered all the calculator stuff for Chapter 11. I'll do a separate thing on Chapter 12. There's not so much calculator stuff on Chapter 12, though. It's really only for the confidence intervals where you're doing the inverse t, and that's about it. Everything else is based on those tables. Anyway, have a good day, guys. See you.